So Ayan Mukhopadhyay is our speaker. He's from IIT Madras. So he will tell us about black hole complementarity from microstate models. Yeah.
Okay, thanks. I thank the organizers first to give me an opportunity to give this talk. Actually, I am also an organizer myself, but not a real organizer. It was an honor to have this day in IIT and have Bal visiting us. And it's a real, so when I joined IIT in 2018, IMSC still didn't have a journal club. Then we started something which was between IIT and IMSC, and Bal was the most enthusiastic participant. And I remember he gave us this fantastic lectures on von Neumann algebras, Riedl theorem, which we learned a lot from. So thanks for being here again in IIT, and it's really an honor to have your happy birthday celebrations here. And so what I will do is talk something which is probably in the interest, although it may not look so from the title yet. So what I will do is to understand this black hole complementarity principle from microstate model. So I would rather begin with a very superficial introduction to it and motivate what we are doing.
So the picture you had in the previous slide has.
Oh, that one. So this is I think from Matisse. So here you see that how inside and outside of a room kind of gets scrambled up. So it's sort of mimics complementary. Okay, so this comes from very early days of 1990s when Stooft started thinking about how black hole information loss paradox can be resolved. And he started with this brick wall and stretch membrane like kind of models, where the idea was that the information is first stored just outside the horizon in a stretch membrane and then released. But then I think a very solid argument came from Susskind, Thodaklius, and Uglum. And he said that what they said that you want to keep 4 principles, and in a full quantum theory of black hole. And these 4 principles are, of course, the unitarity of evaporation process. So the evaporation of the black hole has to be unitary. And there has to be some kind of effective field theory which is valid at the horizon. This is one of the premises of Hawking's original calculation. And then there is something called the fundamental dogma, which is I think a more modern name. It simply says that a black hole to a very outside observer would look like coal as some system with some discrete spectrum. And then there is no drama. Basically, you have equivalence principle valid at the horizon. So these are the 4 things that you would like to keep while resolving the black hole information paradox. And they said that if you want to keep all these 4 principles, then you come to a rather surprising conclusion, is that information gets copied twice, at least for a sufficiently old black hole. So one, it is inside, from the perspective of an infalling observer, it will be inside the black hole. And from the perspective of somebody who is at infinity and is seeing the black hole evaporate away, it will be outside the black hole, and it will come out through Hawking radiation eventually. And no observer can actually verify both copies. And this is important because, of course, in usual quantum mechanics, you have this no cloning theorem, which forbids copying information. But however, as a principle, it's not very, very, very well defined. And this is one of the things that, but basically what is well defined is they wanted to keep these 4 principles. So then there was this famous attack by AMPS and Mathur. This one will never, this red thing will not, anyway, this is okay. So this AMPS and Mathur then came up with some arguments against it, but Mathur was more criticizing not the black hole complementarity itself, but rather whether small corrections can unitarize the Hawking radiation. What AMPS basically wanted to say that, okay, the black hole complementary principle itself is not well defined, but whether you can actually have all these 4 postulates together. And they argued that is not possible by quantum information theory, because if you look at a sufficient old black hole, then in this picture you see A and B are the 2 Hawking modes. One is ingoing and the other is outgoing, and R is a very sufficiently late radiation. So after page time, that is when the black hole, okay, in a very colloquial way, it has emitted half its mass, or the entropy of the outgoing radiation is half of the original entropy. So then B should start purifying R. So B and R has to be entangled, but A and B are also maximally entangled by Hawking's original calculation. And this violates monogamy of entanglement, the statement that a single subsystem cannot be maximally entangled with two subsystems simultaneously. So that's actually the problem. And obviously, there have been many kind of ways to resolve this problem. So I use these two Sanskrit words, Nyaya and Niti, following what Amartya Sen's theory of social justice. So you need two ways to resolve things. One is a matter of principle and also a matter of practice. So in principle, of course, the argument was that after all, these two Hilbert spaces, the Hilbert space of what we call A and R, the Hilbert space of stuff that is inside the horizon and outside the horizon, these actually are not factorizable. So that actually breaks the strong subarelativity argument. And that is sort of, sorry, I can. Okay, so the first way to resolve it is to say that you cannot factorize this to Hilbert spaces. And a more kind of concrete argument was given by Papadimitrios Raju, where they said that the interior is encoded in a state-dependent way at the boundary, in the exterior way. So this is a very concrete argument. And now there are more radical versions of it. We simply say that even if you take a small region and if you have gravity, from the small region will contain the information of everything, however small the region is. Yeah. So of course, there are more radical ways to solve this, but this actually doesn't tell us that where the semi-classical argument goes wrong, or so then actually there was a matter of practice, which practically how you save the complementarity principle, or you save all these four postulates. It was given by Hayden and Harlow, and the argument is as follows: that if you want to actually verify verify cloning of information, you have to first distill the factor RB from R, which will purify B. So you have to first do that. And their argument was that this encoding of information is so complex that it will take time exponential in the entropy of the black hole to just distill this factor, RB, that can purify R, or that can purify B. So therefore, all this thing is not, this paradoxes, no paradox will arise in practice. And recently, Kim, Tang, and Preskill have made the argument more rigorous by introducing pseudo-randomness, which I don't have time to talk about. Yeah, these are, but not that independent actually. I mean, they are sort of connected, because these kind of things about how the complexity of, decoding the interior also appears is similar to this other complexity. Sorry? No, question was whether these two ways are connected. So in this talk, what I will do, I will focus on the how does black hole complementary principle itself is well defined in a microscopic description. So because the principle itself is not well defined, what is more, what people, when they attack the principle, they're actually attacking the four postulates. And then is there a microstate model from where within a local, but not necessarily global? So this I will explain what I mean by the difference. Semi-classical description, where complementarity can emerge, that is, you can copy information twice without encountering any kind of paradoxes. So this is a question that I would rather try to answer. And this will be very similar to a recent understanding of page curve from semi-classical black hole geometry. So people showed that that you can resolve that you can after all get the page curve just from the semi-classical geometry of the black hole itself, although it doesn't see the discreteness of the horizon or anything. Just a semi-classical black hole geometry can be trusted to give the page curve, and even so it doesn't tell you how information is coming out, but at least it tells you that information does come out, and it gives you a Renyi entropy and entanglement entropy of the Hawking radiation, consistent variability. But then can we get a similar understanding of black hole complementarity in this some kind of a semi-classical calculation? And after all, this is whether black hole is a special kind of coal after all, because when you burn coal, you don't end up in anything like a complementarity. So this complementarity is a very, very special feature of the black hole. So now I will talk about information mirroring, which actually is a very good probe of the complementarity principle. So this is an argument that was given by Hayden and Preskill in 2007, and that's quite brilliant argument. So the idea was that you take a small diary D, maybe I have to go up. So you take a small diary D and you entangle with the reference S. This is just simply a tool to make an argument, doesn't play much of a role. And you throw the diary into a big black hole. And it has to be sufficiently old so that there is sufficient number of degrees of freedom E in the early radiation. So when you throw this small diary into the black hole, there is some kind of a unitary evolution happens, which is a random unitary or sufficiently scrambling, sufficiently random U. After which this black hole has a remnant V prime, and a small amount of radiation comes out, which is capital R. So the argument is very simple, that if D is very small compared to B, and R is very small compared to B prime, then you can show that the mutual information between B prime and S is 0. So therefore the entire information or diary is now in R union E. So what it means is as follows. So when you throw the diary, information is automatically immediately coming out of the black hole through some radiation, and this time scale is RS log S. So this is the argument of this. This is called information mirroring, and the point is that if black hole complementarity is true and is consistent with unitarity, then you can decode this diary from R union E without knowing anything about B or B prime. So B is a black hole and E is the early radiation, and U is this unitary process, what happens when you throw this small diary inside. B is a black hole that remains, and this R is a small amount of radiation that comes out. So if D is, so the point is that if black hole complementarity is correct, then you should be able to decode the information without knowing anything about the interior. So that is a very interesting statement, and so we looked into all kind of quantum codes or microscopic models that can demonstrate this, and there was none. In fact, there is only one. There's a model by Kitaev and Yoshida, but they actually require to know something about this capital U or something about this internal dynamics. So we wanted to see if you can have a microscopic model that you do not need. And the other thing is that, as you can see, that when the radiation has come out just now, so it is not in contact with most of the early radiation which is reached the asymptotic boundary. So essentially, if the black hole complementarity is kind of true, and that is that EFT is valid just outside the horizon, you should be able to decode the information only with a limited information of the early radiation. So that is another such a thing. So basically, these are the two things that we would like to see. And but then there is also this question that why, if you are able to decode very easily, very fast, then of course we already know that the interior is scrambled in a very complex way. So how come there are some observables through which you can mirror the information very fast, while information of interior is so well hidden in complexity? And secondly, how come the interior and exterior actually are distinguishable as different Hilbert spaces if they are not in principle? So okay, so these are the questions that we would like to answer. Okay, so I guess I have now to come to the model that we are looking at. So this is sort of an inspired model from something called the fragmentation process that takes place in a near extremal black hole. So all these details are not important. So these are just simply some kind of instantonic solutions in gravity that you can generate. So what happens if you take a big black hole near horizon geometry, which is kind of has some SL2R like symmetry. So ADS2 cross something, and then it can fragment into many different ADS2s. So this is the main picture, and of course this is that you cannot do much control calculation. For the same reason, you cannot do control calculation in Q-city instanton. So for the Q-city instanton, we know what happens when the instanton becomes very large. You get a lot of zero modes, but that's precisely when the Q-city coupling is also large. So you cannot do much calculation. So here you get a lot of zero modes when the throats become sub-Planckian distance, and therefore, that is where gravity becomes strong, and you cannot do any calculation. So basically, what you do is do some kind of inspired model, which is that you think that the horizon has now fragmented into various throats. So suppose the horizon is S2, then you think you discretize S2 into some lattice. At every point in the lattice, you can think there is something like a quantum dot, like an SYK quantum dot, which admits some kind of a two-dimensional gravity description in terms of ADS2. So basically, this is a model. So these are like the hard degrees of freedom. And then, of course, they can interact by these mobile charges, which is the charges or the symmetries of the original unfragmented geometry, and they become gravitational charges that can hover over the lattice. So it's something, a model like this. So more concretely, you have these degrees of freedom. So you have this discretized kind of quantum dots on this, which can be thought of as, so this ADS2 have only 1 degree of freedom. This is described by something called Jacques-Teitelbaum gravity, and the degree of freedom they have is something called the time reparametrization mode, which is the effective mode in the SYK quantum dot system. So every lattice point has some time reparametrization mode, but equivalently you can also say these are these SL2 charges which I write as this curly QIU, and they carry information of the quantum dot state. So so this is a time-dependent state that is parameterized by TIU, or need not be time-dependent, depending on whether the Schwarzian is constant or not. So, and then you have this mobile gravitational air here. It is also SL2R charge, but the difference is that they can simply hover over the lattice, and they will satisfy a Klein-Gordon equation or discrete Klein-Gordon equation. But the overall full system will have only one SL2R symmetry once they start interacting. So let me just write down what kind of equations we use. Okay, this is simply to show you this SL2R charges that you can construct out of the time reparametrization mode. And the mass of each black hole is simply the Casimir invariant of this SL2R charges, which is the Schwarzian of the time reparametrization mode. And so these are our equations. So let me spend some time on it. So the first equation is the equation that tells you how the mass of each site will evolve. So you look here, and the mass of each site evolves using this equation. So if you look carefully, this term looks like the first equation looks like a diffusion equation, but it's a dot product with some Qi prime, because if the hair is time independent, you do not expect any diffusion to happen. So there is a Qi prime there. And this is sort of a simplest diffusion equation that you can write on the lattice. So there is some kind of diffusion of mass. And the second equation, if you just leave out this term, the first two terms is basically like a Klein-Gordon equation, a discretized Klein-Gordon equation. And the second term, so these terms, the reason for writing it as follows, that if you want to see the total conserved energy of the full system, this is simply the sum over masses and the kinetic and potential energy of the hair. So it's a very simple split that you need to have some kind of split between interior and exterior. So this is simplest kind of energy term that you can write down. And so this is sort of the system. This is sort of our equations. Yeah, so you can also derive these equations from some action principle, but which is very complicated. You have to, first of all, do some Liouville-like formulation for each of the time reparametrization modes and write very complicated action. But I simply write the equations of motion, and that's a basic thing that we have. So now we talk about the microstates. What are the microstates of this model? So the microstates are simply the most general solutions this model has, which have where which are time independent or stationary, or static or stationary. So you can easily see that for this kind of throat charges, okay, so let me simply summarize because going back and forth will be difficult. So if you look at the throat charges, one of the components will be homogeneous. And which component is, because there's an overall SL2R symmetry, you can do a global SL2R frame. You can always go to a global SL2R frame where there is a 0th component homogeneous. The two other components are random and constant. So they can be random. So it's like a disordered Ising, it's like a disordered model in that way. So these can be anything in there. But then the hair has this following components. So the hair as such cannot be split into interior and exterior. But in microstates, they allow a split between interior and exterior. So the plus minus components are locked to the hair charges in this specific way, where this capital K is independent of the site is some constant vector. So the plus minus components are locked to the interior, whereas a 0th component has two parts. One is something like a monopole term, and the other one is this radiation term. And this radiation term is simply decoupled from everything and can hover freely without affecting the microstate solution. So there are these kind of splits of the hair, and this is the most general solutions of these equations, which give you static and stationary configurations. And okay, let me skip this part for want of time. So the total energy can now be split in a microstate solution into this following part. So this split is very general. The split between the sum over masses of the throats and the kinetic and potential energy of the hair. In a microstate solution, allows a further split between interior and exterior, because you have the potential part comes purely from the the potential part comes purely from the plus minus charges, and it is locked to the interior. So whereas this monopole term again comes purely from the exterior, and the radiation term comes purely from the exterior. So they basically split up into three parts, into interior and exterior. But however, when it goes from one microstate to another, there is no such split. So when the system relaxes to one microstate, there's naturally a split between interior and exterior. Okay, so now we start with this ensemble of microstate solutions, which you can fix the global mass, the global SL2R, some global charges, and then there are some inequalities you have to further satisfy. I just wanted to say that there are certain further inequalities the charges have to satisfy, so that you have some continuity conditions. And it's interesting, once you do that, then an arrow of time naturally emerges. So either the arrow, so Ti prime is either always positive or always negative for all throats. So you have an arrow of time is uniform. Either it is forward or backward. That naturally comes from this model. So you take one of such microstate, and then what you do is that you throw something inside it. If you throw something inside it, so what happens is that you get some additional shocks. So it basically, these are null matter, but I'm forgetting this ADS2 gravity and writing it terms of only these charges. So basically then you have these are the energies of the matter, of the null matter fields that goes inside the throats, and you can shock them. So what happens is as follows. If you do that, there is something interesting happens, which I first show you. So first of all, the microstate goes to another random microstate. It's go from one microstate to another. And interestingly, almost all of the energy is absorbed by the masses and nothing by the hair. And it becomes better if you include more and more sites. So this is another one picture, what is happening. So you start with one microstate where you have some collection of Qi plus and some collection of Qi minus charges which are random. They relax to another set of Q plus and Q minus charges, as you see. And this is only with a single shock. You see, it's quite a very random, it goes randomly from one to another. And the 0th component always relaxes, again, homogenizes. It has to, because as I said, in a microstate, the 0th component should be homogeneous. So basically, here you see that you actually go from one microstate to another. And here is the mass distributions before and after the shock. So basically, then you create some decoupled Hare oscillations that decouple from the microstate and hover around. So it's a very pseudo-random dynamics, and it behaves like a classical black hole. How much time I have? Okay. So it behaves very much like a classical black hole. So where you have if all the energy is absorbed and there is quick relaxation from one microstate to another, it has very pseudo-random behavior, and there is a decoupling of exterior interior is also happening dynamically, because once you relax to a microstate, the energies decouple. You have split into interior and exterior components. And so now I talk about classical information mirroring. Again, for want of time, I will just simply go a little fast. Let's not go through all this too much detail. So you have something like this. So you have a microstate solution, and then you can try to throw in information, now only classical information. And the way you throw in classical information is that you throw in information as an ordered list. The ordered list is time sequence and locations of shocks. So which of the, suppose you have 5 sites in your model, so which site you are shocking and in which order. So that becomes like 1, 4, 5. You first shock 1 first, then shock 4, then shock 5. So that carries some information, and this is the information that you're throwing in. Then one microstate goes to another microstate where the radiation component decouples. And actually, you also need the early radiation. The early radiation is simply the monopole component. And using that, only the information of the global monopole frame, that's only information that you can need. You can decode it. The most important thing about this decoding is that when you decode, you are not allowed to know the initial microstate, what the initial microstate was. That's the most crucial thing. And so that, whether it works, so you can do this with the normal modes, the phase differences of the normal modes. So there are certain observables in the decoupled radiation that you can do it, and that is how it occurs. So the initial microstate is very random and inhomogeneous, but after the decoupling, when you look at the Hare, if you look at the phase differences of the normal modes, then you see some approximate symmetry where this one, which has the highest phase difference, is the site that you shocked. And similarly, if you cite 2 shocks, whether they are like this or like this, you can also look at the largest phase difference and the smallest phase difference. Here again, you see some kind of cyclic symmetry, and it decreases from here to here. And then, so these are the 2 things that are shocked. And you can also say which was shocked earlier, which was shocked later. That depends whether they're neighboring sites or not. So importantly, when you do this decoding, you don't need to know what is the interior, what was the interior state, what was the initial microstate, at least for this observable. So now what we can do, so far I basically talked up the microstate without talking about Hawking radiation. You can now allow each of these throats to evaporate or into Hawking radiation. And that is something that you can do like in the AEMM or recent page curve models. You simply allow some bulk matter field to exist in each of these throats. And this bulk matter fields, when you give transparent boundary conditions, they radiate away. They create Hawking radiation into some bath. And then you just simply take this, and the masses of each throat decay exponentially. And the interesting thing that happens is that while the thing is radiating without shocking it or anything, the system automatically homogenizes. The Q0th component automatically homogenizes. So you go to some kind of a adiabatic decaying microstate. And then if you look at the plus and minus components, they actually also homogenize, but on a much longer time scale. And they go to attain a common null frame with an overall scale that is fixed by the pre-existing boundary condition. So essentially, what happens is that something very interesting happens. So you might think it's very boring, because all the information is lost of the initial state, because everything homogenizes. And furthermore, the throats homogenize to a null frame, and all information seems to be lost in the interior. The throats decouple from each other at very late time, and so does Hare from all the throats. This is precisely what we need for copying information. But actually, this is what we understood, that although this sounds like a puzzle, that everything is homogenizing, everything is decoupling from everything, it looks like we are losing information. But this is precisely what you need for a black hole complementarity principle to work. But for that, you need to go to the quantum. You cannot just look at the classical picture, to go to the quantum picture. And this is what is the most exciting part actually of the talk, for which I have only 5 minutes left, probably 5 or some. So I will basically come here. So what happens now? So you can go to a single throat and ask this question. So what happens if you couple something like a classical harmonic oscillator to a black hole? What happens is exactly what you expect, is that the classical harmonic oscillator damps out, it goes to rest with x and p equals to 0, and all the energy goes inside the black hole, right? If you take a quantum harmonic oscillator, then also this happens. Expectation value of x, expectation value of p goes to 0, but the system does not go to a ground state. It actually goes to not even an eigenstate, it goes to a quantum trajectory. And this quantum trajectory and the black hole ring down pattern will carry information of the initial state in a double copy. So let me explain this a little bit. So, okay, this is simply a pictorial representation. So very quickly, so let me show you exactly what we are doing in this very simple setup, is that you have a mass, there is a black hole throat which has some time-dependent mass to satisfy this equation on the right-hand side. And this O is an operator that is dual to some bulk field, which is phi. And then if you're not familiar with ADS-CFT, that you don't need to follow all the details here. Essentially, there is a Q, sorry, I wrote something wrongly. This should be X, not sigma X, is simply lambda expectation value of X. The harmonic oscillator that lives at the boundary. And then the expectation value of the harmonic oscillator gives you a boundary condition for this bulk field phi. It should be X, not sigma X. And then you self-consistently solve. The most important part is this Schrodinger equation. You can also do it for a mixed state that you need to satisfy and do everything self-consistently. There's an overall conserved energy for the full system. But without and then there is a way to solve the oscillator, the harmonic, the equations of the oscillator. A very simple, very, very nice way. I think some similar methods were discussed by Kumar in yesterday. But I have to skip this. I just simply show you the result, what happens. If you look at the expectation value of x and p, it still goes to 0, right? But you see, and then, okay, the expectation value of O also goes to 0. If the expectation value of x, if the expectation value of xp and the O goes to 0, then you see that both systems decouple from each other. And if you decouple from each other, whether you are in an eigenstate or not, the energy of individual is conserved because it are independent Hamiltonians. And then, so the energy is conserved. So you see, importantly, although the oscillator is losing energy, doesn't lose all its energy. Of course, classically, it should go to 0 because classically, if x and p equals to 0, expectation of x, expectation of p is equal to 0, then the energy is also 0. So it should drop down to 0. But quantum mechanically, no. Quantum mechanically, see that there is some interesting residual energy left. While the black hole gains energy, but not the full energy, the total energy is, of course, conserved, and this is the energy of the interaction. Okay, so what happens is as follows. Let us look at let us look at what happens after everything settles down. So what is the quantum state of the oscillator after it settles down? So without going through derivation details, I give you the answer, is that you start from, suppose a superposition of the ground state and excited state. It's like a qubit, and these are the these are the angles on the block sphere. Then the time-dependent state or the quantum trajectory that comes out of this is okay. I have to define these objects. So this is basically a coherent state. So I have to define this. So these are the psi 0 t. So this is some displaced. These are the displaced energy eigenstates. So there's an xpt, and there is an xpt. That's only, and there's a ppt. So these are the psi 0 and psi 1. But they satisfy the usual classical equation. Xp and pp is simply xp dot. But now I said expectation value of x is 0. So expectation value of x will be xpt plus something. And this xpt has a solution which is a cos omega t plus b sin omega t. So if you know capital A, capital B, you know the output quantum trajectory explicitly. But you see, in order for the expectation value of xt to go to 0, you should choose capital A and B according to the input angles on the block sphere. So the output quantum trajectory will know exactly what you started with. So it encodes, although in a non-linear way, it's a non-isometric encoding, if you put it that way. But the output quantum trajectory would know exactly the original qubit that you started with. And you might wonder, where is the copy of the information? So you see that when the black hole is ringing down, settling down to a mass, you see that it's oscillating, and the amplitude of the oscillation is also going down. So you can encode the two block angles also here. So the way to do it is that the amplitude carries information of the initial energy, and the phase carries the information of the initial phase. So there's an amplitude to energy and phase to phase map. So the black hole ring down actually. So we have two copies of the same information, or two copies in these two decoupled quantum trajectories. So, or you can say quantum algebras. I'll explain the connection later. So you have these two different decoupled things from where you can actually get the full information of the initial qubit completely. Actually, it's important for this to occur that you start with a small input space. If you start with a very large input space, this will not happen. But okay, I can come back to. Okay, so this is what you see very interestingly. Now we can go back to the microstate and see the relevance of this. So now if you start with a three-state model, three-site model, you have the hair, you can quantize the hair, that's what you can easily do. Then you can also couple some entangled qubit to two of the sites. So you quantize hair, you quantize bulk scalar, but you still treat locally, you treat gravity in a semi-classical way. You allow Hawking radiation. Now what will happen is that all the quantum trajectories of the hair, the three sites, the two qubits, everything will decouple from each other. That's what is going to happen. So now what to actually see, the way to see it is in the language of Hong Liu and Leuthezer, is that you have a large number of quantum algebras in the full thing. So each sector depends on kind of quantum algebra that is preserved by time evolution. So that's a more general way of speaking, because instead of going to semi-classical to the full quantum theory, so you will end up with large number of quantum algebras. But these quantum algebras are not necessarily commuting with each other, because if you do something here, it will again excite everything. But interestingly, you basically copy the initial information of the full state, initial information of what you're throwing in of the qubits, everything many times, and then encoding several copies of the same information. So you can do some. So it allows you to process some kind of parallel processing of information if you want to be clever how to do it. So basically now we are figuring out many things, like how mirroring occurs, whether you can do how much of processing we can do without destroying the information completely, how complex encoding of initial state occurs, like although the mirroring is occurring very fast, you can mirror without knowing the initial state. If you want to know the infalling qubits, you can simply dig it out without knowing completely what the initial state was made of. And then how will you actually do the complex encoding of the, how to decode this initial state. And at some point of time, effective field theory will emerge at the horizon when you have the more of a classical description of the microstates possible, like I said in the beginning. And when does it break down? So these are the questions that you can actually now you can actually ask in this simplified model. And so I just simply end with conclusions and outlook. So we have a reasonably good phenomenological model of a quantum black hole that gives insights into origins of black hole complementarity while exhibiting right classical behavior. So it has this energy absorption and relaxation property. And horizon here plays a very crucial role to see how split between interior and exterior occurs. Then you see that although when you make it Hawking evaporate, you seem to lose everything information of the initial state. But actually what happens is that the mutual decoupling of all degrees of freedom actually creates many quantum trajectories, or rather quantum algebras, that are preserved under time evolution independently. And it copies information without leading to cloning paradoxes. So this provides a new way to encode several copies of information in distinct quantum algebras, each preserved by time evolution. Perhaps we can control this process of decoupling, and then we can do a new way to understand or designing some quantum information processes in the future. Okay, so I don't want to drag further, and I thank you for your attention.
Thank you, Ayan. Maybe one or two short questions, quick questions.
Yeah. So it's not cloning because the cloning is cloning into a state. Yeah. But here the cloning is, the copying happens in two ways. It's a property of like the algebras that describe the. So in a way you see that. So here the output trajectory. So this actually is this capital AB are classical parameters that are labeling this output trajectory. But it's not really a particular, so it's not really like a cloning in the usual sense. It's more like that you have to study an algebra to be able to dig it out. Like what is the property of the algebra that acts on this state? So you have to define it that. So, okay, a more precise definition he wants to do it in a more precise way. So which I don't have like so much time, but another way you can see it in this black hole ring down. It's let's say a type 3-1 algebra that comes in, right? According to Liu. And recently we have been able to understand the decoding also by using non-equilibrium correlation functions and looking at the fluctuation dissipation relation between them, which evolves with time. So that also is something like an algebra. So it's put in an algebra rather than in a state.
Yeah.
Well, yeah, in a way you can think about it. Maybe, yes, I've been thinking about it in that way. So it could be that you can simplify the dynamics using some kind of hydro plus stuff. There could be some kind of similar approach. Yes, there could be a simplification of this.
Quantum field theory, quantum states cannot be localized. This is the Richelieu theorem. Now there are new developments which one can prove quite easily, that on the horizon of the black hole there is a whole lot of there is a set of observables which intertwine non-separable inequivalent representations of the algebra. So the Richelieu theorem comes if you represent the observable algebra irreducibly on the. So there is stuff that is living on the horizon intertwines inequivalent representations, which if you try to put them together, it is a non-separable Hilbert space. There are plenty of states. You can define entropy, whatever. But I tried it, but I don't get the Hawking formula, but I get entropy. So
that's interesting.
Seems to me that classical ideas are not appropriate in this context. One should purely talk in quantum language in terms of observables and states and see what happens.
Yes, yes.
Yeah.
So here what happens is somewhat.
There need to be no semi-classical approximation at all. Why do we believe semi-classical? The word out there is quantum, it's not classical.
So here we do not use the usual global semi-classical approximation. We are kind of doing it only locally. So it's a fragmented geometry. But already we see features of what you are seeing, because what you are talking about, because what I said that there are these different quantum algebras. Like you can see each of these decoupled quantum trajectory is actually a kind of quantum algebra that is preserved under time evolution. So time evolution preserves some kind of, you can think of like sub-algebras. And they are not commuting with each other also, because if you do some probe in one, it affects other. But it's something similar to what you're saying. That's kind of emerged from the dynamics of them. Yeah.
Maybe due to shortage of time, others can ask during the lunch break to Ayan. And let's thank Ayan again.